So hello, everyone. I'm Kayla Brzezinski, the Assistant Director here at the Museum of the White Mountains. I'd like to welcome you all and thank you for attending our virtual lecture this afternoon. Before we begin, we all live on Indigenous lands. So the Museum of the White Mountains is located on Ndakina, which is the ancestral and present homelands of the Abenaki and Wabanaki peoples. We are grateful for their stewardship of these lands and waterways. In seeking to better understand this region, we also seek to learn from Indigenous elders and hold space for their voices. To learn more about the Indigenous histories of your place, visit native.land.ca, and to learn more about the Abenaki peoples, visit the Musée d'Abenaki in Odanak, Quebec, or their website at museedeabenaki.ca. I will put these links into the chat shortly. But before I do, I would like to pass it over to Dr. Eric Kelsey to introduce us to today's speaker. So thank you.
Thank you very much, Kayla. It's my pleasure to introduce to you Dr. Angela Desjardins, who is a solar physicist and associate research professor at Montana State University. She grew up in Bozeman, Montana, and earned her bachelor's, master's, and PhD in physics from Montana State University, and loves it so much she's sticking around there. And she wears many hats. She does many things, and just touching the surface, she's the chair of the National Council of Space Grant Directors. She's the director of Montana Space Grant Consortium, and the director of Montana NASA EPSCoR, a program to stimulate research in Montana. I've got to learn more about Angela and talk with her on numerous occasions over the last couple of years. And she's an amazing person, as you will see. She has an incredible passion for science and science education. She likes to use space and our unique perspective of the cosmos from Earth to ignite the human sense of wonder and imagination in young people, primarily college students, but other groups as well, including high schoolers. And she focuses on involving underrepresented and disadvantaged people. The fortuitous timing of the last several solar eclipses that we've had across North and South America have served as Angela's foci for several grant projects to achieve her goal of sparking students' imagination and wonder, which brings us to the Nationwide Eclipse Ballooning Project, which is actually an iteration from past eclipses that have occurred over the last 10 years that Angela is leading, and we'll discuss today. And Plymouth State has been fortunate in that we have participated in this project, and it is the topic of the current exhibit at the Museum of the White Mountains that is on display now from now until December 13th. So if you get a chance, please go on over and check it out. So we are grateful to have Angela to join us today during her dinner hour, because she is in Zambia at the University of Zambia, and she is there through a Fulbright scholarship to help establish a new master's in science degree program in space science and applications. And after her presentation, we'll have time for questions for Angela. So hold on to those questions. And now I'd like to hand it over to Angela.
Great. Thank you, Eric. I appreciate that. Thanks everyone for joining today. I'm looking forward to talking with all of you, and I guess I'll be talking to you for a bit, but excited for the question and answer period. That's often one of my favorite when I hear what kinds of things that you're curious about. As you'll see in a slide, a couple in curiosity is actually very important to me and very important to science. So yeah, as Dr. Kelsey mentioned, I'm actually joining you from Lusaka, Zambia. I'm here for almost a year on a Fulbright, as a Fulbright scholar. If you haven't heard of that program before, it's a great program that offers people at many different levels, from students all the way up to people who have been professors for a long time, opportunities to act as ambassadors in a way to like 130 different countries around the world to go have an opportunity to spend some time there and bring knowledge back to the US from what they learned there. The reverse is also true. The Fulbright program also brings some people into the US from other countries, but primarily it's people from the US going to other countries. The focus of today's talk is not on that, but if anyone has questions for me about that program, I'm happy to share that as well. So with that, I'm going to share my screen and share some presentation slides because what I do is really so beautifully focused on visual things. I definitely have to have slides, although sometimes, you know, it's actually better not to have slides, but in this particular case, it's a good thing. So this is my title slide, and oftentimes, you know, we think about title slides as, they're just kind of a placeholder and not really something that you spend too much time talking about. But this slide actually means quite a lot to me, and so I wanted to spend a minute just talking a bit about it. So here are a bunch of different logos for different organizations that made what I'm going to talk about today possible. And in the background is actually an image from the recent total solar eclipse from one of our engineering balloons. So we have that context of eclipses from the edge of space, and then all these wonderful logos. So our logo is there on the left, and then we are sponsored by NASA, and so that's a prominent logo. And then the next one on the top row there is the Science Activation Program. So the funding that we have for our program is partly through the Science Activation Program, which is an education program that's run through the NASA Science Mission Directorate. But then it's also partially sponsored by the Space Grant Program. And so I'm the director of Montana Space Grant, and there are space grants in every state plus DC and Puerto Rico. And the space grant programs are primarily focused on higher education, but do some other things as well. And then we have all of these other wonderful logos for the people who make this project possible. And we have our wonderful Plymouth State University there as one of them. We couldn't do this project without all of these different people pulling together to make it happen. And one of my favorite parts of doing this project is getting to work with all of these great people. So that's part of what makes this slide not just a throwaway for me. Okay, so if I can, there we go. Just a quick overview of what I plan to talk about today. I'm going to talk to you a bit about what our project is, then share a few of the results from analyzing how we met our education goals, because this unique project is really equally education and science. It's doing this groundbreaking science that couldn't be done without a large group of people. And it happens to be that this large group of people are students. And so the project is a little bit unique in that way. In some ways, people call our project a citizen science project, which, you know, basically means you have a big group of people doing science. But in a lot of ways, the project isn't really citizen science because it's primarily at higher education institutions, and in some case, a few high schools. But in that way, it's more formal education, the formal learning process, even if it's not necessarily coursework. And also, citizen science typically means that it's a pretty low step for anyone to be able to participate who wants to. And that's not the case here. The project is actually pretty highly technical, and getting the equipment and supplies necessary to participate, while inexpensive compared to things like satellites, is relatively expensive. So I just put that in context that the project is a pretty unique one. It's somewhat similar to citizen science. It's somewhat similar to regular science, but then also has this really important education piece. So I'll talk about that a bit. I'll talk about some of the science results and then talk about what we're still working on. So to start putting in context why we're doing this crazy ballooning project, I want to share this chart. So in the National Science Foundation, or NSF, they do these surveys every year of people in the general public in the US about common misconceptions in science. And a lot of these questions they ask on a repeating basis so that they can ascertain how these misconceptions are changing over time. And one of the questions that they ask every 5 years is, does the Earth go around the sun, or does the sun go around the Earth? And so this particular result was from the 2014 survey that was done asking this question by NSF. And it found that 26% of the American public thinks that the sun orbits the Earth. And you might be sitting there, feeling a little bit shocked by that statistic. But if you think about it, it really isn't that shocking, right? As humans, what we know is what we see for the most part. And what we see every day, or every day that it's not cloudy, is we see the sun come up, go overhead, and go down, right? So the sun goes around us. And unless you paid attention in science class when you were looking at your two-dimensional textbook and it showed the little diagram of the sun in the center and the planets going around the sun, then you probably didn't necessarily completely internalize the fact that that's not actually the case, right? It might appear that the sun is going around the Earth, but actually the Earth goes around the sun. And so I saw this statistic in 2014, and it really got me to thinking about, oh man, like, how can we change this? It makes sense that we have this misconception, or some people have this misconception, but how do we go about changing it? Like, what can we do to maybe change the needle on this to not be, 26% of the American public, or 1 in 4 people thinking that the sun orbits the Earth? And at the same time, I have to tell you another story. And that is from when I was a kid. And so when I was a kid, I was a big space nerd, like I am now. It started when I was very young. And I had this astronomy book that had all kinds of interesting information in it. And it had a list of dates of total solar eclipses across the world over the next many decades. And just to date myself, this is like in the mid 1980s when I was a kid, looking at this awesome astronomy textbook. And I was looking at these dates of the total solar eclipses and learning about what a total solar eclipse was, and just being fascinated by, oh my gosh, wouldn't that be amazing to like see the sun go dark in the middle of the day? Man, like I really want to see a total solar eclipse. So let me look at this list and see when the next time is that I can see a total solar eclipse. And I grew up pretty poor. And so my mentality at the time was that for me to see a total solar eclipse, it would have to be in the United States. And so I was looking at the list, and I kept looking down the list, looking down the list, looking down the list. And then finally I got to a total solar eclipse in the United States, and it was in 2017. And so here's this, 8-year-old girl in small town Montana, in the mid 1980s, and looking at the date 2017 and thinking, like, I remember honestly thinking like, oh, 2017, like, am I even going to be alive in 2017? That's like so far from now. Like, I don't even know if I'm ever going to be able to see a total solar eclipse, because 2017 is just so far away. But I think that stuck with me, right? This in the back of my mind, that we have this opportunity to have a total solar eclipse in 2017. And of course, as we got closer to 2017, then putting together that the eclipse was coming up in 2017 with, wanting to maybe do something about this misconception about the sun going around the Earth, And then the fact that we do a lot of ballooning at Montana State University is kind of where the idea was born from to do the project. Okay. Okay, so this quote is one that I really like and really is the motivator behind what we're trying to do as well. And that is that while learning in courses is really important, it's maybe even more important in my book, but I'm biased, of course, that to really give students the input that they need, the experiences that they need to know if they've picked the right field, or if they do know that they've picked the right field for their career, to give them some experience, some real workforce experience. We need to involve them in the kinds of research that we're doing. So if we tell them, like we often do in courses, right, they're probably going to forget. And if you can somehow show them things, a lot of courses do, involve students in a little bit more of a showing, not just a telling way, they may not remember, but if we involve them, then that's when they'll truly be able to understand. And so that's a lot of what I do in my career, is trying to make opportunities for students to be involved in science, so that they can really understand what they're working on and if they're in the right place for their careers. So I wanted to just take a minute and describe what we mean by ballooning. So if you haven't heard of scientific or stratospheric ballooning before, then maybe you have really kind of no idea what I'm talking about. Although, the whole like Chinese balloon situation from, a little over a year ago and still more recently has helped people understand what we mean by ballooning, right? Before that, not too many people knew, but after that, people are a little bit more in the know about what we mean. But basically, stratospheric or scientific ballooning is a really great way for relatively low cost to get experiments up into a space-like environment where you have the vacuum and the temperatures similar to an environment like where you would have a spacecraft. And it takes a lot of multidisciplinary work, like all kinds of different people working together to make these things happen. And I love that at Plymouth State University, we have an entire team in the Nationwide Eclipse Ballooning Project that are art majors. I think that's absolutely wonderful. And the whole process is really mission-like. And so even if people don't want to go into something where they would be doing missions, that kind of structure is really informative. And so having all of these opportunities makes ballooning a really wonderful opportunity. And so you can see a picture there on the right-hand side of, this is more what we call like an engineering balloon, right? Where students build the payloads and put them on balloons, and the payloads have different experiments, often cameras and that kind of thing. It's attached to a parachute, so everything comes down on a parachute, so it doesn't come down and completely break apart. And typical flights go up to about 100,000 feet and last about 2 hours. So just coming back up to speed a bit on the history. So the first eclipse that we did with the project was the 2017 one. And some firsts there were the first to live stream a total solar eclipse from a space-like perspective. That was a big goal of that particular project, was to live stream the view of the shadow of the moon on the Earth. But we were also the first to fly a constellation of balloons across the continent. And that success from 2017 led into funding from the National Science Foundation to continue, this time outside the US, with the next eclipse that happened in July of 2019. And we just sent one team down there from Montana at that particular time. And with this eclipse kind of shifted more towards the science. And so where 2017 was really focused on the lighting and the images, in 2019, we really shifted toward, there's some, really amazing science that we can do, understanding how the atmosphere responds to the cold, dark shadow of the eclipse. And indeed, we had a Nature paper that was published from the work there. We detected, had confirmation of detection of stratospheric gravity waves. And I want to just take a second to mention what we mean by gravity waves. I have some pictures that I'll show later on. But if you've ever seen like bands in the clouds, those are gravity waves that are set up by things like temperature changes or things like mountain ranges, and shouldn't be confused with gravitational waves. So two totally different things, right? Gravitational waves are tiny ripples in the fabric of space generated by things like interacting black holes and things like that. So that's gravitational waves. That's not what we're talking about. We're talking about gravity waves that are generated by disturbances in the atmosphere. So that success led to more funding from the National Science Foundation, where we involved 4 teams from 4 different states, and to go down to South America again, because there is a nice coincidence. It's actually not completely a coincidence. We could talk into the whole how eclipses occur and those Soros cycles and all that kind of thing. But anyway, there's another eclipse again in South America in December 2020. But as you know, a little thing happened in 2020, and you can see the people in the picture there are wearing masks, even though it's outside. And if you think back to that time, yes, we wore masks outside during that time. And so that definitely interfered with our plans. We had originally planned to have 2 sites in Argentina and 2 in Chile. But basically, the Argentinian government was completely unresponsive, and we weren't able to send teams to Argentina, but we did send 2 teams to Chile. And then, unfortunately, there was a little thing called an atmospheric river, which you probably also might be aware of, and it is what it sounds like, huge deluges of rain. And so actually, a lot of the research that happened that, you know, was published from the eclipse effort in 2020 was about the atmospheric river. And not as much about the eclipse effects, because it became not impossible. We did see some gravity waves from that eclipse, but the data just got really messed up from having that atmospheric river in 2020. But an atmospheric river had never been studied as well before as when we did in Chile in 2020. So that was interesting in and of itself. So then that brings us to the present effort, where nature handed us this really wonderful opportunity 7 years after the eclipse in 2017. Then we had another total solar eclipse in the US in 2024. And not only did we have 2 eclipses in 7 years, but we had it was a pair of eclipses, an annular solar eclipse in October, and then the total eclipse just 6 months later. And you probably all know this because it has now happened, but right, an annular eclipse happens when the moon is actually too far away from Earth to completely block out the sun. And so we still have a rim of the sun around the moon. And so it doesn't get dark, right? We don't have quite the same effects in an annular eclipse. But a total solar eclipse, right? We get the darkness, we get to see the atmosphere of the sun, and it's really very cool. So this time with our project, we divided our teams into 2 tracks. One was the atmospheric science track, which is the one that the Plymouth State University teams were on. And the other one is the engineering track. And the difference here really is kind of like it sounds. One's a little bit more focused on science and the other one's on engineering. The atmospheric science teams were really focused on understanding the atmospheric response to the cold, dark shadow of the moon from the eclipse. And so they used these little devices called radiosondes. And you can see in the picture, the gal is holding in, well, the hand that it's her left hand, right? But on the right, holding the parachute and the derailleur that allows the instrument that's in her other hand with the antenna sticking out to fall below the balloon so that the wake of the balloon doesn't cause an issue. And then all of the instruments for these are in that little device in her other hand that measure location, wind direction, wind speed, humidity, and temperature. And so that gives us some really great information about the weather and about the conditions. And so in fact, actually the National Weather Service has 93 different stations across the US. And these are the exact same devices that they fly at least twice a day, every day, that give us our weather forecasts. And, you know, those in the program there at Plymouth State University, right, they know all about doing that kind of thing. But this is one of the big parts that enables us in the country, and it's similar thing is done around the world, to be able to look at the high level atmosphere and be able to predict the weather. On the other side, on the engineering, the focus is more on students building their own payloads and getting images and different things like that. Although the engineering team was also wanting to gather information to help us understand about the atmospheric response, but gathered that information a little bit different way, including the visual information. And then the project is also broken down into pods. So one of the things that we learned from our previous experiences, especially in 2017, is that obviously the more support that we have in smaller groups of people, the more effective and easy it is for people to participate successfully. And so we had 9 different pods, 4 for the atmospheric science group and 5 for the engineering. And then each of the teams was part of one of the pods. And the main leadership team then worked with the pod leads, as we called them, who then worked with their teams. And it created a nice community to be able to have people to work together. So you can just kind of see a diagram of where the different institutions and pod leads were across the country. So just a quick word about some numbers. So we had 53 teams and over 850 students participating on those 53 teams. On those 53 teams, some were more than one institution on a team working together. And so we actually had 75 institutions, and 30% of those institutions are minority serving institutions, and 15% were community colleges. As I think was mentioned in the introduction, one of my passions and a big focus of the project was including institutions that hadn't done ballooning before and were underserved institutions and underserved students. And so it was a big focus of ours to train teams who hadn't done this kind of thing before, so they might be able to continue doing this kind of activity in the future. And 38% of the students were an underrepresented gender, and 23% were an underrepresented minority. And all told, 63% of our participants were underserved in gender, minority, or institution. So in order to make sure that we were being as supportive as we could so that there was the best chance for having a successful outcome, we put a lot of attention and detail into the learning resources. So this is a very busy slide. I don't intend for you to be reading all of the things in the background there, just was trying to give a flavor. We created many different opportunities for students and teams to be learning. So we created online courses, and in many places, teams actually had official courses that were taught, like temporary special topics courses based on the course material that we provided online. Not every team did that. It was optional, but all of the resources were there that were basically independent courses, one separate one for atmospheric science and one separate one for engineering, with all of the detailed information that would be needed to be able to be successful in the project. We also had monthly pod meetings led by the pod leaders. And we had an online forum, we had remote talks from experts. Yeah, we really did a lot to make sure that we were providing everything we could for the teams to be successful. But, you know, in doing such a wild scale project like this with so many different people and was, you know, really very highly technical, it was a really challenging project. And the project being challenging was actually one of the things I think that was good about it. If you think about it, if participating in the project were straightforward and easy, then it wouldn't have been as interesting. And so actually doing something challenging, doing something cutting edge, doing something that no one had done before was one of the things that makes the project really rich. And so I alluded to this before, this is one of my favorite quotes by Einstein is, the true sign of intelligence is not knowledge, but imagination. And sometimes you could call that curiosity. Curiosity and imagination are really the most important part. And so having a challenging project where students are encouraged to use their imagination to fuel their curiosity, that's really where the beautiful part of the project comes in. And so just some of the challenges, right? Trying to get all of the students to the paths, the path of annularity and the path of totality. Yeah, that's a challenge, and it's also a risk, right? Anytime you travel, especially via road, right? That's a challenge. Getting helium, we're actually having a helium shortage in the country right now, so that was a major challenge to try and make sure all of the teams got helium where they needed helium. And then the cost, right? So we provided through the grant a good portion of the cost, but we couldn't, the grant would have had to have been so much bigger, and it was a good size to begin with. So much more money if we were to, pay the people leading the individual teams or pay the students. But a lot of the state space grants helped with that part. But yeah, the cost is not insignificant. And then time, right? You have to balance wanting to start the project early, but also recognizing that it's the nature of students to only be in a particular location for a relatively short point of time, and wanting students to be able to feel like they could participate in the entire project before they had to move on to their next step. So balancing that time and how much time it would take to prepare was a challenge. And then just technically, right, there's lots of detailed techniques, both in the science, like how we carry out the campaigns for the atmospheric science side, how we build all the payloads and make everything be successful on the engineering side, was quite challenging. But as I said, lots of challenges, but that's part of what makes the project so rich. Okay, so now I want to just talk about a few student outcomes. So we have really wonderful evaluators as part of this project who conducted many different surveys of the students, of the mentors for the teams, and of the leadership team. And I just wanted to share, there's lots and lots of things I could share, but there's 3 outcomes from the students that I wanted to share. So this is the first one. So this question asked, if the students were interested in obtaining a STEM degree or certificate. And the green here, that on the right-hand side, basically the students indicated that participating in the project made them more interested in obtaining a STEM degree. And the orange here, which is the next largest one, is the same amount. And you can imagine, right, that the students self-select to participate in this project. So a lot of the students who self-selected to participate in the project were already, quite interested in obtaining a STEM degree or certificate. But it's actually quite meaningful to me that more than 50% of these people who already self-selected to be part of this project indicated that the project made them more interested in obtaining a STEM degree or certification. I think that's a wonderful result. And then somewhat similar, but slightly different, I'm interested in pursuing a career in a STEM field. So again, nearly 60% of the students said that participating in the project made them even more interested in pursuing a STEM career than they had in the past. So this is one of my favorite, or one of the things that makes me most proud about this project. And this is a little bit complicated, so I can explain it well. We asked a question about their STEM identity. So basically, how much overlap do they see between themselves and someone who is a STEM professional? Do they see, hardly any overlap in their identity as being a STEM professional? Or do they see a lot of overlap? Do they already identify as a STEM professional? And we asked the students to think back to before they participated in the project and after. So this survey was given after the total solar eclipse. And so you can see here, looking at the before, so looking back to before being participating in the project, which is in blue, you can see that the highest response, more than 45% of the students said that, they saw almost no overlap between themselves and a STEM professional. But then you move to the post after participating in the project, and you can see that a huge percentage, nearly 70% of the students, saw large to almost complete overlap between themselves and a STEM professional. So participating in the project changed a vast majority of the students from feeling like they weren't STEM professionals to now feeling like they identified as a STEM professional. And that's quite meaningful to me. And then taking that idea kind of one step farther is this question: how did the project make them feel in their confidence and ability to get the job that they want after graduating? And so same kind of thing here. Blue is looking back to before participating in the project, and the orange is after participating. And you can see here, if you look just at the blue, right, more people always said that already had said that they felt confident or very confident about getting the job that they desired. But you can see that it was somewhat mixed, right, between very unconfident and neither confident or unconfident. But after, very few students felt unconfident about getting the job that they wanted. And nearly 80% of the students who participated said that they felt confident or very confident in getting the job that they wanted after participating. So again, I think that's very meaningful and says that we achieved what we wanted to achieve. Okay, now I wanted to switch to science goals. And so here's a picture of gravity waves actually generated from a total solar eclipse. So in both the annular eclipse and the total eclipse, we saw some wonderful gravity waves just on the ground. So this picture is just from the ground, looking up. And so this is what I'm talking about. You can kind of see the bands and the clouds, and that's a signature of gravity waves. So the main science goal was to understand the atmospheric response. And by understanding the atmospheric response in the special case of eclipses, it helps us to understand the atmosphere better in general. And better understanding the atmosphere in general helps us to do things like predict the weather. And of course, what's happening in Florida right now it tells us how important it is to be able to predict the weather. And it also helps us to understand climate change better. And so this is just one small step that we can do to help better understand the atmosphere. Okay, so these charts are really quite technical. I think you should be able to see my cursor here, but just wanted to share some actual data. So this data I'm about to share is from a SuperSite team from the annular eclipse in New Mexico, and the Plymouth State University teams were part of this SuperSite group. And the SuperSite group was able to launch one of these radiosondes instead of just once an hour, every hour, 24 hours before the eclipse and 6 hours after, like most of the other teams. Because there were 4 teams together, they actually launched a radiosonde every 15 minutes. And so we're able to get really good time resolution data. And so a couple other things to point out on these graphs before I explain what's happening. There's some vertical lines here. So this dashed one indicates the sunset. So like I said, they started doing the flights 24 hours before. So this indicates sunset. The solid red line here is the sunrise. And then the dashed black line indicates the start of the annular eclipse. And then the solid black line is when the annular eclipse was happening. And then this is the far right-hand side is the end of the annular eclipse. So, and these give here, these particular charts that we're looking at here, give the temperature in degrees Celsius. And the height in kilometers. And so the temperature is the color coding here. You can see the different temperatures here. And so it's really very cold, right? So the warmest that we see here is minus 51 degrees Celsius, and the coldest is, about minus 70 degrees Celsius. And then height, right, we go up to about 30 kilometers in height. And then we have time on the x-axis. And what we see here in the left-hand panel, you can kind of see these bands here. And those are actually signatures of the gravity waves. And if we look at the panel on the right-hand side, what we're seeing here is a global smooth model of what's happening in the atmosphere around the whole world. And it's data combined with a model. And basically, the telling result here is that in our actual data, we see the signature of the gravity waves. You can kind of see these bands here. But when you just do this smooth global model, we don't see those bands, right? The smooth global model doesn't show those details. It just kind of shows generally what is happening in the atmosphere. And so this is a result that tells us that the gravity waves were present as a result of the eclipse. And then similarly, this now, instead of looking at temperature, we're looking at the north-south flowing wind. And again, our data is on the left-hand side, and this model is on the right-hand side. And here you can see, again, there are these bands in the actual data on the left-hand side that are gravity waves. And you don't see those bands in the global smooth model. And so this is another indicator that actually seeing the gravity waves in the data shows us that they were generated by the eclipse. And so while we had some evidence of the gravity waves from the event in Chile in 2019, because we didn't have as detailed of time data and the careful way that we went about it this time, this is really the first confirmed evidence of eclipse-driven gravity waves in the stratosphere. And this paper about this will be submitted for publication very soon. Okay, and so now I've been talking about the results from the atmospheric science side, and now I'm just gonna switch to quickly talking about some wonderful things that happened with the engineering teams with the visual data. So this is some images from a 3-dimensional or 360-degree camera on one of the balloons. So almost all of the teams flew these 360-degree cameras where you can look all around and up and down and in every single direction. And you can see here the shadow of the eclipse. And these are all just snapshots from the same particular frame. So all at the same time, but looking in different directions. And so you can look up at the balloon, you can look down at the payload, you can look down at the ground, and this one in the lower left is actually, looking straight down at the payload. And then if you look in the bottom right, you can actually see the eclipsed sun in that frame. And so here's from another team, that 360-degree video flattened out. And so you can recognize, you can see the shadow of the eclipse approaching here. But it actually wraps all the way around. And if you view this footage with VR goggles, it's absolutely amazing. It seriously makes you feel like an astronaut. It's absolutely amazing. And I'll show you a link where you can see that video if you happen to have a VR headset, or even a simple one, right, where you can put your phone in one of those simple headsets. I encourage you to look at some of these videos because it's absolutely amazing. But this is flattened out so you can kind of get a feel. And so as it comes, I want you to watch as the shadow is coming. You can actually watch the sun kind of wink out. You can't see it in too much detail, but you can see how it goes from something somewhat brighter to this dim eclipse. And I'll let it play one more time. But you start to get a feel of what the view looks like from these balloons. You can actually see the curvature of the earth and the blackness of space. It's a really very special vantage point, especially when seeing the shadow of the moon on the ground. It's just really quite spectacular. And a lot of the other evidence that we're looking at with the engineering teams is looking at the visual evidence for the gravity waves. And there was some other special things that were done on the engineering side. I could talk about this for 24 hours, but I'm basically out of time. So I'll just conclude with what's happening now. So we have so much data that we're about to make public. So one of the things that's important in being a NASA-sponsored project, and it's good to do anyway, is making sure that we share all of the data that we collected so that anyone who wants to look at the data and analyze the data can. And so publishing that data publicly will be done here very soon, actually in the next week or two, hopefully. And the data analysis is ongoing. As you can imagine, like working to analyze all this data takes quite some time. And there will actually be quite a few papers that'll be published on all of this work that we've done. And so, yeah, writing articles and lots of doing what we call knowledge sharing, you know, sending students to conferences and things like that so they can share the work that they've done. And we're actually about to embark on something that we're calling the continuation project. So a new exciting activity for this particular academic year where some atmospheric science teams will be pursuing a project looking at the Gulf Stream off the east coast of the US. And some engineering teams will be looking at the radiation environment high above the Earth as a result of the solar maximum that we're approaching in 2025. And then, of course, we're really working to make sure that we can maintain all of these wonderful networks that we've built. And we plan to propose to the Science Activation Project, again, to continue the ballooning collaboration, not with eclipses, because we don't have any more eclipses in the US coming up until 2044, but to continue the collaboration doing ballooning campaigns. And so I'll conclude there. I'll leave this up for a minute before I stop sharing my slides and ask questions. This particular QR code brings you to those science figures that I was mentioning and those 360 videos. So if you're interested in checking those out, you can you can use this QR code to bring you to that particular page. Or if you just search for eclipse and balloon, you'll find our website and there's a link on the front page that brings you to where the videos and figures are. So I'll stop there and I'm gonna turn on my video. I haven't gotten a warning again in the last bit that my connection is unstable. So hopefully, I will be able to leave my camera on and I'm happy to take questions.
Yeah, everything's been smooth with the audio and video since that first little hiccup.
Okay.
Yeah.
Okay, good.
Yeah, if anyone has a question, please click on the React button at the bottom of your window and click Raise Hands and go ahead and ask away. I'll call on you to ask your question.
Yeah, and if you don't want to speak anything out loud, you can also write into the chat, and we can filter questions that way as well.
Here is a question from Tanner. Did you ever lose sight of your passion? And if so, how did you create that spark again? Great question.
Yeah, I like that question. I'm often, wanting to ask technical questions, but I find myself a lot of times asking the more personal questions, right? Because sometimes that can be the most insightful. So thank you for your question. I would say, like any person, I have sometimes lost sight of my passion temporarily. And that typically comes when I feel overwhelmed, right? So, you know, lots of different things happening. Like, in fact, today I got to go meet the Minister of Technology and Science for Zambia today. And all these different things happening, you know, today. And then he's going to join us when we go visit the National Remote Sensing Center tomorrow. And, you know, just so many things happening right now. And sometimes, right, like I can let myself get overwhelmed, and it's like, you know, what am I doing? Like, I'm so tired. Like, but then usually all it takes is, you know, a student asking a really good question or something like that. And the tiredness or overwhelmed goes out the window, and I'm feeling passionate again. But yeah, I think I would just add you I'm maybe giving you more than your money's worth, but yeah, I think finding your passion is really one of the most important things that you can do. You know, maybe you've heard the quote that if you're doing something that you really enjoy doing, you'll never work a day in your life, right? And I'm one that really believes strongly in that. I mean, sometimes work is work, right? Like no job is without its struggles. But if you find something that you're really passionate about, then that can make a complete difference in your life. So encourage you, if you're still in school, or even if you aren't still in school, to find what makes you tick and pursue it.
Great. Any other questions?
I can take a stab at one. So Angela, this is a great presentation, and I have a wife who also studied science, but seems to have liked to have branched out beyond science into more interdisciplinary moments. I imagine when you were growing up, you were probably thinking you were going to be a scientist, but I imagine, I mean, I'm just guessing, just based on my personal experiences, that there must have been a moment or a series of moments where you realized that the hardcore science wasn't what was attracting you, and something slightly different was, like staying with the science but doing it differently, like the engagement, the outreach. Can you speak to that moment, or those, how that feels, or what you know, just to the people here, that many of them are actually still students trying to figure it out?
Yeah, no, it's a great question. Yeah, you know, and again, maybe I'm gonna give you more than what you really wanted, but you know, I didn't actually know until I was a senior in high school that to go into astronomy, the way to go about it was physics. I, you know, to that point thought that to go into astronomy, I had to find an astronomy degree program. But it wasn't until my senior year when I was taking a physics class that my teacher was like, no, the better way to do it is to be a physics major, right? And then you can, you know, take some astronomy classes. I mean, there are some astronomy degree programs out there, but you know, if you really want to be a serious astronomer, you need to first just do physics. And so that was the first illumination that, like, oh, I need to do physics to do astronomy. And then I would say I was a little bit of a late bloomer in realizing what you're talking about. I didn't really realize until like my last year of graduate school that what I had picked to do graduate school in didn't really float my boat. And that's true in really a lot of fields, right? So in solar physics, so my background is in solar physics, and to make any very small incremental progress, which in most science, like, you know, what you're doing for your PhD or things like that, you're making very small steps, which are really important. But what it meant for me was basically sitting behind a computer all day, every day. And that just wasn't me. And I had some opportunities to interact with the Montana Space Grant in the past and do some like outreach and working with students and that kind of thing. And there was an opportunity at the time to work with someone who I greatly admired, who was running Montana Space Grant at the time. And so I thought, oh, you know, let me take a year and work with this person that I greatly admire and see if going like a little bit more the education route is something that I'm more suited to than sitting behind a computer all day, every day doing my research. And I absolutely loved it. And there was no turning back. And so, yeah, it's a really great question. Actually, one of the things I really encourage students to do is to try as many different things as possible, so that you might know earlier than I did, in the last year of your PhD program, that what you picked is actually something you enjoy doing. And asking lots of questions, right? Like, of people who are in the field that you are planning to go into, what every day is like, and what makes them tick, like the question that Tanner had about, being passionate. And yeah, getting as many experiences as you can about what it actually means to be in that field, so if it's suited to you. And some people are absolutely suited to sitting at the computer doing coding. A lot of it was the coding, like, to be honest, like, I'm not, coding is not my favorite, and to be active in that field, I really needed to do that. But we need all different kinds of people, and finding the area that fits who you are is important.